College Algebra Chapter 3, Section 7, Topics in the Theory of Polynomial Functions, Part 2. Fundamental Theorem of Algebra. When it comes to complex zeros, it can be shown that if a plus bi is a zero of a polynomial function with real coefficients, then so is its complex conjugate, a minus bi. This brings us to the conjugate zeros theorem, which says if p of x defines a polynomial function having only real coefficients, and if a plus bi is a zero of that polynomial, then the conjugate a minus bi is also a zero. This tells us that imaginary solutions never travel alone. They will always come in pairs, the a plus bi and the a minus bi. If 1 plus 3i is a solution, 1 minus 3i must also be a solution. So, if we're going to find a polynomial having zeros 3 and 2 plus I that satisfies the requirement p of negative 2 equals 4. If you want to, pause this recording, give it a try, and then resume the recording to see how you did. Okay, we know that since 2 plus I is a 0, then 2 minus I must also be a 0. A general solution is going to be p of x equals a, some number out front, times x minus 3, that's the first 0, times x minus 2 plus I, that's the other 0 they gave us, times x minus 2 minus I, which is the conjugate of the 0 they gave us. Then what you have here is the whole thing being multiplied out. Multiply out the, when you're doing this, it's better to multiply out the x minus 2 plus I and the x minus 2 minus I first and get rid of your i's early on. But when you multiply these out, you have a times x cubed minus 7x squared plus 17x minus 15. Now we need to find that a, that number that's out in front that we don't know. We know that p of negative 2 is 4, so we're going to put in negative 2 for all of our x's and 4 for our p of x or our y value. And then we can solve for a. And you see we're doing that here, and we get that a is negative 4 over 85. And when we multiply that through, we get negative 4 over 85 x to the third plus 28 over 85 x squared minus 4/5 x plus 12 over 17. You may be uncomfortable working with fractions, but you do need to get more comfortable with that. Remember, you do have a calculator that can help you multiply and convert to fractions, and I would be sure to use this if you need to. So the fundamental theorem of algebra tells us that every function defined by a polynomial of degree 1 or more has at least one complex zero. It can be real or imaginary. If p of x is a polynomial of degree 1 or more, there's some number k such that p of k equals 0. In other words, there is some number, either real or imaginary, that you can put in the place of x and get 0 as your answer. Another way of putting it is that there is some number that is an actual factor of p of x. There is some number that you can have where p of x equals x minus k times q of x, and q standing for quotient, where q can also be factored, resulting in p of x equals a times x minus k1 times x minus k2, etc., until you get to the final factor. In other words, you can break up any polynomial into a series of factors where all of the x's are to the first power. In order to do this, your zeros may not all be real. You may have some imaginary in there, but it is possible to completely break up a polynomial into factors where x is to the first power in every factor. Now, I've already talked about the number of zeros, and this is really something that we've said before. A function defined by a polynomial of degree n has at most n distinct or unique complex zeros. For example, we're going to find all the complex zeros of this function. they're giving us that 1 minus I is a 0, so they're giving us a starting point. Why don't you pause this recording and give this a try? Now I'm going to give you a hint. You're going to want to use division, synthetic division, to help you out with this. Pause the recording, give it a try, and resume the recording to check your answer. So the first thing we do is we divide out the 1 minus I. And as you see here, when we do that, we have 1, we have minus 6 minus I, 11 plus 5I, minus 6 minus 6I, and then 0. So we see that it is indeed a factor, which no surprise they told us that. Notice how we do the imaginary numbers, the synthetic division with those. It's the same idea. We brought the 1 down, then we multiplied it by 1 minus I, and put that under the negative 7. Now since the negative 7 doesn't have an imaginary part, we just added them, added the real parts, and got negative 6 minus I. Then it gets a little tricky because you have to multiply the minus 6 minus I times the 1 minus I, which means you need to FOIL it out and you need to work carefully. When you do that, you get negative 7 plus 5I. Again, add the real parts. And again, we're going to end up having to FOIL it out. When we do that, we get 16 minus 6I. And when we add that to negative 22, we get negative 6 minus 6I, which gives us negative 12. And our solution at the end is 0, which tells us that it is, again, a 0. What we're going to do is we're going to divide out 1 plus I, because according to the conjugate zeros theorem, if 1 minus I is a 0, then 1 plus I must be also. And here you see us dividing like we did before. This one's a little better because since we have the i's in place, when we do our multiplication and our addition, we get these nice numbers at the bottom. We don't have any more i's left over. So we end up with a 1, a negative 5, and a 6. So now we're down to a quadratic. We started with a quartic. The first time we divided, it got us down to a cubic, which is what we're have here. And when we divide by the 1 plus I, we're left with a quadratic. Remember, every time you divide out a factor, the power of the polynomial goes down by 1. So now we have x squared minus 5x plus 6, which we can factor pretty easily. And when you do that, you get 2 and 3 for those zeros. So this whole big polynomial factors into x minus 2 times x minus 3 times x minus 1 minus I times x minus 1 plus I. And you see the 4 zeros listed there. Okay, multiplicity of a zero refers to how many times the zero appears as a solution. For example, if you were to factor this 6-degree polynomial, you would get x times x plus 2 squared times x minus 3 to the third. We only have 3 distinct or unique solutions. We have x equals 0, x equals negative 2, and x equals 1. The power on the parentheses there tells us that the negative 2 is actually doing the job of 2 factors. It's x plus 2 times x plus 2. So we have one number that's serving as the solution for 2 separate factors. So we say that negative 2 has a multiplicity of 2. X minus 1 to the third. Again, this means x minus 1 times x minus 1 times x minus 1. So there's actually 3 factors that all have a solution of 1. That means that 1 has a multiplicity of 3. So we're going to find a polynomial function with real coefficients of lowest possible degree, having a 0, 2 of multiplicity 3, a 0, 0 of multiplicity 2, and a 0i of single multiplicity. So we have 3 zeros, 3 unique zeros. We have 2, we have 0, and we have I, and we're going to create a polynomial out of this. Why don't you pause this recording, give it an attempt, and then resume the recording to see how you did. Okay, so here we have it. Our 0 of 2 is going to give us a factor of x minus 2. It has a multiplicity of 3, so we put a third power on it. The 0 of 0 with multiplicity 2, that's just x, and that's going to have a square. And then we know that we have x minus I, and since we have x minus I, we must also have x plus I. And then all that's left is to multiply this mess out, and we get x to the 7th minus 6x to the 6th, plus 13x to the 5th, minus 14x to the 4th, plus 12x to the 3rd, minus 8x squared. Now this is just one function that would satisfy this, because you could actually multiply any number except for 0 through to everything and have a different function that will actually meet these conditions. So this is the most basic function that you can get that meets the requirements. Now we're going to look at the behavior of these zeros and compare that, look at that in light of their multiplicity, and see if we can get some conclusions. So the first one we're going to look at is x plus 3 times x minus 2 squared. And this is what it looks like when it's graphed. What I want you to look at is where x equals negative 3 and y is 0. And notice what's happening there is the graph is crossing through the x-axis. But notice where x equals 2. It's not crossing, it's just touching the x-axis at that point and then going back up. Keep that in mind. Okay, slightly different function this time. And notice we're using the same zeros. This time we have negative 3 has a multiplicity of 2. Look what's going on where x equals negative 3. It's touching the x-axis and then dropping back down. And this time x minus 2 has a multiplicity of 3, so the number 2, we see that it's crossing the x-axis, but there's also something else going on here. Notice the curvature. As it approaches the x-axis, it's kind of curved downward or concave downward. And then as it leaves, it kind of takes a swing back up, so it's curved up again. So it's actually changing how it's curved as it crosses. Okay, one more example. All right, a little more complicated this time. We've got some different numbers here. X squared, that's your 0 there is 0. And notice at 0, 0, it's just touching the x-axis. At x minus 1 has a multiplicity of 1, and our 0 is 1. So when x is 1, it's crossing through. And then when we have x plus 2 squared, it's touching and then going back where it was. So it's just touching the axis and coming back down. Okay, so what we've seen in these examples, if a 0 has a multiplicity of 1, the graph will cross the x-axis at the x-intercept. If it has an even multiplicity, the graph is tangent to the x-axis. In other words, it's touching it, but it doesn't cross it. It just touches it and then goes back in the direction it came from. Now, if it has an odd multiplicity that's greater than 1, it actually does both. It crosses the x-axis and it's also tangent. We see that little flattening out as it changes how it curves. So it changes the concavity at the x-intercept, and it does cross through. So whenever you see an even multiplicity, the graph is actually not going to cross through the x-axis there. It's just going to touch it. Odd multiplicities, they will cross, and if it's an odd multiplicity greater than 1, not only does it cross, but it actually changes the concavity or how the graph curves. Illustrations of that, you could see A is where we have a multiplicity of 1. B represents multiplicities that are even. And then C illustrates the odd multiplicities that are greater than 1. So by observing the dominating term, and remember what we mean by the dominating term is that term that should be in the front, the one with the highest power on x. By observing that and noting the parity of multiplicities. Okay, parity again means even or odd. So we're looking at the very first term, the term with the highest power on x. We're looking to see if the multiplicities of the zeros are even or odd once it's been factored. And looking at these two things, we can draw a rough graph of the polynomial by hand without using our calculator. So we're going to try that. We're going to sketch p of x equals negative 2 x plus 4 squared times x plus 3 times x minus 1 squared. Pause the recording and give it a try, and then resume the recording to see how you did. Okay, our dominating term is negative 2x to the fifth. Now, we know that the negative 2 is obvious. Why is it x to the fifth? Well, we have our first x is going to end up being squared. Our second one is to the first power, and our third one is going to end up being squared. So 2 plus 1 plus 2 is 5. So negative 2x to the fifth. The main thing there is that it's a negative in front, and it's an odd power, which means that as you look at the graph going left from the center, it's going to end up going up. And as you look at the graph from center toward the right, it's going to end up going down. So that gives us, first of all, an idea of our end behaviors. Now, as we look at our factors, we have zeros of negative 4, negative 3, and 1. Negative 3 is a multiplicity of 1, so the graph is going to cross through the axis at negative 3. Negative 4 and 1 are both even multiplicities, so the graph will touch there but not cross through. And then we also have that the y-intercept is negative 96. The y-intercept is where your x values equal 0, so you put in 0 for all the x's, and that's how you find that. So if you can see on the left, there is a kind of a general graph drawn. It's not necessarily going to be very precise, but it's going to have the major points that are correct. So you see that it's rising to the left, it's falling to the right, it's touching at negative 4 and positive 1, it's crossing through at negative 3, and it definitely hits the y-axis at negative 96. And you see the dotted lines there because we really don't know if there's any other strange behavior going on in the graph. It's a fifth degree, which means it can change direction up to 4 times. So 1, 2, 3, 4. We found all the direction changes. So it looks like it's a pretty good graph. And then if you look at the one on the right, this is one that's actually graphed on the calculator. It looks like we did a pretty good job graphing by hand. The rational zeros theorem provides us with a method of creating a list from which any real rational roots for our polynomial will come. Now that doesn't mean that all of the numbers on the list will be roots for our polynomial. It doesn't mean that any of them will be. What it does mean is that if we have real rational roots, they will come from the list. How we're going to do that is we're going to take the factors of our constant term, which is the last number, the one without the x, and we're going to put those factors, each of them, over the factors of the leading coefficient. We did this in Algebra 2 and Algebra 3. What we're going to do is we're going to work an example. Here's our polynomial. We want to list all the possible rational zeros. We're going to use a graph to eliminate some of them. And then we're going to find the ones that actually work, and we're going to factor this polynomial. Why don't you pause the recording, give this a try, and resume the recording to check your answer. So first we're going to start with making our list. We need the factors of 2 and the factors of 6. We're going to put the factors of 2 over the factors of 6, and we have a list of 6 rational numbers. Looking at our graph, we can rule some of these numbers out. The zeros don't go below negative 2, and they don't go above positive 1. So we can eliminate some of the numbers from there. It says also negative 1 is clearly not a 0, since the graph does not intersect at the point negative 1, 0. So we can eliminate negative 1. And C, we're going to show that 1 and negative 2 are indeed zeros because they look like it. So we're going to try those out by dividing. We'd use synthetic division to divide by the 1. And indeed, we get a 0 remainder. Then we use synthetic division on what we got after that division to divide out the negative 2. And again, it is a 0. Now we have 6x squared plus x minus 1, which we can factor. And we get that x is negative 1/2 and 1/3. And you see there the results, the factoring. Okay, we're going to look at Descartes' rule of signs. Now, I want you to have seen it and to have gone over it and understand it. The good news is that you are not going to have to actually use it on any of your homework or test or quiz. Let me explain what it is. Descartes' rule of signs says that if we have a polynomial p of x, with real coefficients and a non-zero constant, and it has the terms are in descending powers, in other words, it's in standard form, then the number of positive real zeros either equals the number of variations in sign occurring in the coefficients of p of x, or is less than that by a positive even integer. In other words, what you'll do is you'll look at the polynomial and you'll count how many times the signs change from positive to negative or negative to positive. That count tells you how many real positive coefficients, real positive zeros you could have, or it could have less than that by 2. So if you end up counting and you get 3, it means you could have 3 real positive zeros, or you could have 1 real positive zero. Now you can figure out the negatives in a similar manner. What you do is you put in a negative x for all the x's, and you simplify it. What that means is if you have an x to an even power, that negative x is going to end up being positive after all. So you put in negative x for all your x's, and you do the same type of count. You count how many times the sign changes between negative and positive, and then the number of real negative zeros could either be that number or less than that by 2. I'll show you how this works. Here we've got p of x, and we're going to first of all figure out how many positive real zeros and negative zeros it could potentially have. The positive real zeros, what we're going to do is we're going to count the sign changes. So it starts positive, it's positive x to the 4th. It changes to negative, so that's 1. Then back to positive, and then it stays positive, and then it goes to negative. So there are 3 changes in the signs. That means we could have 3 positive zeros, or 3 minus 2, we could have 1 positive zero. You see that here. For negative zeros, it's a little weird because what you have to do is put in a negative x for all your x's. And for anything with a 4th power, it's really not going to change anything. It only affects the odd powers. So as you can see, it really only made a difference. It made a difference in the sign in front of the 6x to the 3rd and in front of the 2x. So now we're going to count the sign changes again. It starts positive, it stays positive, it stays positive, then it changes to negative, and then it stays negative. So we only have 1 sign change, which means that there could only be 1 negative real root. And what's done with Descartes' rule of signs, what you can do with it is create a chart showing the number of positive zeros that you could have combined with the number of negative zeros you could have, and then you throw in any imaginary zeros, and it just kind of tells you what your potential solutions could look like. We also have a boundedness theorem, and again, you're not going to have to actually perform this, but I do want you to be aware of it. It says that let p of x define a polynomial function of degree n-1 with real coefficients and with a positive leading coefficient. If p of x is divided synthetically by x minus c, so you're dividing it, and if c is greater than 0 and all the numbers in the bottom row of the synthetic division are non-negative, 0 or positive, then p of x has no 0 greater than c. If c is less than 0, if it's a negative number that you're dividing by, and the numbers in the bottom row alternate their sign, 0 is considered positive or negative is needed, so you can call 0 either one, whatever's needed, then p of x has no 0 less than c. So what it does is as you're working these problems, and this was really more of a concern before the technology got to where we are now, it would actually give you a boundary where you knew, well, I don't have to check numbers greater than this or less than this because my answers have to be inside of that. So it kind of gave you some limits and made it narrow down your choices when you were trying to determine the zeros. So we're going to talk through this one. It says show that the real zeros of p of x equals 2x to the 4th minus 5x to the 3rd plus 3x plus 1 satisfy the following conditions. No real zero is greater than 3, so we're going to divide by 3, and no real zero is less than -1, so we're going to divide by -1. And here we go. So we divide by 3. In our result, we have all positive integers at the bottom. And that's what the boundedness theorem says. If you have that as your result, then you know none of your zeros are going to be greater than 3. When we divide by -1, notice how the signs alternate. And this is what, again, the theorem says. This means that we have no zero less than -1. Okay, the rest of this video is just going to be some extra practice for you. So my suggestion is that you pause the recording to try these problems and resume the recording to check your answers. Continue in this manner through the rest of the recording.